The AI that recognizes your face, drives our cars, and even helps doctors is, well, it's incredibly powerful. But what happens when it has to look at a bad picture? A blurry, grainy, or just plain messy one? So today, we're going to dig into exactly that, how a new generation of AI holds up when the images it sees are less than perfect.
So here's our game plan for this explainer. First, we'll set the stakes and see why clear AI vision is so critical in our messy world. Then, we'll meet the AI contenders, these powerful transformer models. After that, we're going to put them through a pretty brutal distortion gauntlet, check out the scoreboard, and finally, break down why these results really matter for the tech you use every single day.
All right, so to kick things off, let's talk about a really fundamental challenge. The AI models we hear so much about, they're usually trained on these pristine, super high-quality images. But here's the thing. The real world isn't a perfect, clean data set. It's messy, it's unpredictable, and it's almost never that clean.
And this isn't just some abstract technical problem. No way. When an AI's vision gets compromised, the consequences can be incredibly serious. I mean, we're not just talking about your phone tagging the wrong person in a photo. We're talking about things like safety, health, and just basic reliability.
Think about it for a second. An autonomous car has to be able to see a pedestrian through thick fog or pouring rain. In a hospital, a radiologist might be relying on an AI to help spot a tiny tumor in a medical scan, where, image clarity is everything. Security systems need to accurately identify faces in low light, and in a factory, an AI might be the only thing that spots a microscopic defect on a circuit board. In all of these cases, a failure to see clearly could be absolutely catastrophic. So who are these AI brains we're putting to the test? Well, let's meet the main character in our story today, a revolutionary type of AI called a transformer. I'm sure you've heard of them. They're the engine behind models like ChatGPT. But trust me, their power goes way beyond just words.
Basically, at its heart, a transformer is an AI that's just brilliant at understanding context. So when it's reading text, it figures out how all the words in a sentence relate to each other. And when it's seeing, it does the exact same thing, but with the different parts of an image. This lets it intelligently focus on the most important details to figure out what it's looking at. It's pretty cool.
So here's a quick peek under the hood. First, the AI basically chops up an image into a grid of small patches. Then, and this is the magic part, it uses this powerful technique called self-attention to weigh the importance of each one of those patches against all the others. Finally, it makes its prediction based on the patches it decided were the most relevant. It's a really, really effective way to see.
But not all transformers are built the same. Not even close. On one hand, you've got these absolute heavyweights, like V-Large, with over 300 million parameters. You can think of parameters as the little individual dials the AI uses to learn. And on the other hand, you have these nimble, lightweight models like MobileViT, designed specifically for your smartphone with just over 1 million parameters. The difference in scale there is just immense.
So keeping those different models in mind, researchers at Nokia Bell Labs decided to put 22 of them to the test. They created this brutal digital obstacle course, an image distortion gauntlet, really, to see how these different AI brains would handle some serious visual stress. Okay, so every good experiment needs a starting point, right? A baseline. They started with a perfectly clear, high-quality image from the famous ImageNet dataset. This is the ideal scenario, what the AI is supposed to see. First up in the gauntlet, blur. They applied a Gaussian blur, which basically simulates what happens with an out-of-focus camera lens. It just smooths out all those fine details that the AI might be relying on. Then they added noise. This is called additive Gaussian noise, and you'll recognize this effect. It looks a lot like the graininess you get from a photo taken in a really dark room, where the camera's sensor is just struggling to pull in enough light. Next up was a totally different kind of noise, called salt and pepper. And you can kind of see why, right? These random black and white pixels, they mimic the kind of errors you might get from a faulty sensor or maybe a bad data transmission.
And finally, they hit the images with the most common distortion of all, the one we all run into pretty much every single day, heavy JPEG compression. This is what happens when you save a file over and over again, creating all those blocky, pixelated artifacts.
So, after this digital torture test, we get to the big question. How did the AIs actually do? Well, the results revealed some fascinating, and in some cases, some pretty dramatic weaknesses.
Now, this is really interesting. Look what happened to the lightweight models. This chart here shows their accuracy against that grainy Gaussian noise. You see those purple and green lines that just take a nosedive? Those are the MobileViT models, the ones designed for our phones. Their ability to correctly identify the image just completely plummeted as the noise got worse.
And this really highlights a huge trade-off in AI design. On one side, you've got efficiency. You need the AI on your phone to be small and fast and not drain your battery, right? But on the other side, you need robustness, the ability to perform reliably even when the conditions are bad. This research shows that in the process of making these models mobile-friendly, they also became a lot more fragile.
But hey, it wasn't all bad news. When it came to that super common problem, JPEG compression, the researchers actually found something pretty surprising. They noted what they called a consistent robustness right across the board.
So check this out. This is the crucial point. Look at how stable the accuracy is for almost all the models as the JPEG quality drops. They hold up incredibly well. But, and this is a big but, once that quality level gets really, really low, we're talking below a level of 10, their performance suddenly falls off a cliff. It seems like transformers can handle a ton of compression, right up until the moment they suddenly can't.
So what does all this mean for the AI we interact with out there in the real world? Let's bring it all together.
All right, so here are the key takeaways. First, even our most advanced AI vision can be surprisingly fragile when it runs into real-world messiness. Second, there's this constant trade-off, this battle between the efficient AI we need for our phones and the super robust AI needed for high-stakes jobs. And finally, this all shows that just making AI bigger isn't enough. To make it truly reliable, developers have to train it on the same kinds of imperfect, unpredictable images that it's actually going to face out in the wild.
And this all leads us to one final, kind of provocative question. We carry this incredibly powerful AI around in our pockets every single day. But knowing how sensitive it can be, especially these lightweight versions, you have to ask yourself, is it truly ready for all the challenges the real world is going to throw at it?